This video is about caching. We are finishing the data layer. Every LLM API call costs money and takes time. Caching is how you avoid paying for the same answer twice. By the end of this video, you will have a working cache in front of your AI endpoint that returns stored answers in about 1 millisecond for zero cost. Let's see, what is it? Here is the core problem. When users ask your AI application similar or identical questions repeatedly, you are making a fresh API call every single time and paying the full cost every single time. Caching stores the AI's answer the first time a question is asked. The next time someone asks the same question, you skip the API call entirely and return the stored answer from a fast in-memory database. The user gets their answer in 1 millisecond instead of several seconds. Think of it like a FAQ page on a website. The first visitor asks what your opening hours are. You call the AI, get a clear and accurate answer, and save it. The next 500 visitors ask the exact same question. Instead of making 500 API calls, you serve the saved answer 500 times instantly. One API call served 500 people. For applications with repetitive queries, customer support bots, documentation search, FAQ tools, caching can reduce your API costs by 40 to 70%. The key tools are Redis, which is a fast in-memory key-value database, and HashLib, which is a Python standard library for creating hash functions. A hash function takes any input and produces a short fixed-length string that uniquely represents that input. Next, workflow. The caching workflow has 5 steps. Step 1. A request arrives with the user's prompt. Step 2. You hash the prompt to create a cache key. Hashing means running the prompt text through a mathematical function that produces a short, unique identifier. The same prompt always produces the same key. Step 3. You look up that key in Redis. Redis is a key-value store, which means it works like a Python dictionary, but runs as a separate server process, and is much faster and more durable than a dictionary in memory. Step 4. The cache hit path. If the key exists in Redis, you return the stored answer immediately. This takes about 1 millisecond and costs 0 API tokens. Step 5. The cache miss path. If the key does not exist, you call the LLM as normal, get the answer, store it in Redis with a TTL, and return it. TTL stands for time to live. It is a number in seconds that controls how long a cached answer stays valid before Redis automatically deletes it. This appears in the tip at the bottom of the slide. The 2 boxes at the bottom compare what happens in each path. A cache hit is instant, free, and feels the same to the user as a real LLM call. A cache miss runs the normal LLM call and stores the result, so the next identical request will be a hit. Next, key concepts. 3 things to understand deeply. First, cache key design. The cache key must include every input that could affect the response. If you only hash the prompt text, but 2 requests use the same prompt with different system prompts, they will get the same cached answer, even though they should get different ones. Include the prompt, the model name, and the system prompt in your hash input. Use SHA-256 hashing, which is a standard cryptographic hash algorithm that produces a 64-character string. Use sort keys equals true in JSON.dumps to ensure the same inputs always produce the same JSON string, regardless of dictionary insertion order. TTL controls how long a cached answer stays valid before expiring. Match it to how often your underlying content changes. For live data like prices or stock levels, use a short TTL of 5 to 60 minutes. For product documentation, 1 to 2 days is reasonable. For stable company policies, a week or more. Never cache responses that are personalized to a specific user, because serving one user's cached answer to a different user is a serious privacy problem. Third, Anthropic native prompt caching. This is a different kind of caching that happens at the API level. If you send a long system prompt on every API call, Anthropic can cache the processed version of that prompt on their servers. Subsequent calls that use the same cached system prompt are charged at 10% of the normal token cost. You enable this by adding a cache control field to your system prompt with the type set to ephemeral. Ephemeral means temporary. The cache lasts 5 minutes on Anthropic servers. Next, project setup. Install the required packages. Redis for the Python Redis client, Python.n for loading your API key, FastAPI and Unicorn for the web server, and Anthropic for the LLM. Start Redis using Docker. Docker is a containerization tool that lets you run software in isolated environments without installing it directly on your machine. The command runs a lightweight Redis container and maps port 6379 on your machine to port 6379 inside the container. Port 6379 is Redis's default port. Verify Redis is running by opening a second terminal and running Redis CLI ping. The Redis CLI tool is Redis's command line interface. If Redis is running correctly, it prints the word Pong. If you cannot install Docker or Redis, Slide 8 shows a pure in-memory alternative using a Python dictionary that requires no extra tools at all. Let's create cache.py file. This file contains 3 functions that everything else uses. The make cache key function takes the prompt, model name, and system prompt as inputs. It serializes them into a JSON string using JSON dumps with sort keys equals true, which ensures consistent ordering, then runs that string through SHA-256 hashing and prepends the prefix LLM : to the result. This prefix makes it easy to find all LLM cache entries in Redis using pattern matching. The getCached function takes a key and calls cache.get on the Redis connection. If the key exists, Redis returns the stored string. If the key does not exist, Redis returns none. None in Python is a special value meaning the absence of a value. The setCached function takes a key, a value, and a TTL. It calls cache.setX, which is Redis's setWithExpiry command. setX stands for set with expiry. It stores the value and tells Redis to automatically delete it after the TTL seconds have passed. Let's create main.py file. This is the complete FastAPI endpoint with caching wired in. The route handler has a clear 3-part structure. First, build the cache key from the incoming message and model name. Second, call getCached with that key. If a cached answer exists, return it immediately with a source field set to cache. Third, if no cached answer exists, call the LLM, store the result using setCached, and return it with source set to LLM. The source field in the response is extremely useful during development. When you make 2 identical requests and the first returns source LLM and the second returns source cache, you know your caching is working correctly. The ask model includes an optional TTL field with a default of 3600, which is 1 hour in seconds. This lets callers override the cache duration per request if needed. Next, in-memory cache. This slide shows how to build a cache using only a Python dictionary. No Redis, no Docker, no extra installs required. This is perfect for development or when you want to test the caching pattern before setting up Redis. The _cache variable is a module-level dictionary that acts as the cache store. Module level means it is created once when the Python file is loaded and persists for the lifetime of the server process. The cache get function retrieves an entry from the dictionary. It checks the expires at timestamp against the current time. If the entry has expired, it deletes it from the dictionary and returns none. This is called lazy expiration because expired entries are only deleted when someone tries to read them, rather than on a timer. The cache set function stores a value with an expiration timestamp, calculated as the current time plus the TTL in seconds. The important limitation is at the bottom of the slide in the tip. This cache lives in process memory, which means it is lost every time you restart the server. For anything beyond local development, use Redis. Next, Anthropic native prompt caching. This slide covers a different kind of caching that saves money specifically on large repeated system prompts. The use case is specific. You have a long system prompt, perhaps 2,000 or more tokens of detailed instructions, company policies, or examples, and you send it on every single API call. Without prompt caching, those tokens are billed at full price every time. With prompt caching, Anthropic processes and stores the system prompt on their servers for 5 minutes. Any call during those 5 minutes that sends the same system prompt is charged at 10% of the normal input token cost. The code change is small. You change the system parameter from a plain string to a list containing a dictionary. That dictionary has a type field set to text, a text field containing your system prompt, and a cache control field with the type set to ephemeral. Look at the cost comparison box on the left. Without caching, 100 calls with a 2,000 token system prompt costs the full price for 200,000 tokens. With caching, only the first call pays full price. The other 99 pay 10%. That is a 90% reduction on system prompt costs. Next, testing your cache. This slide shows 3 ways to verify caching is working. The first test uses curl. Make the same request twice. The first response should have source set to LLM. The second response should have source set to cache. If you see this pattern, caching is working correctly. The second test does the same thing in Python, using the request library, measuring the time difference to confirm the cached response is much faster. The third approach is Redis CLI, the Redis command line interface. The KES command with a pattern lists all matching keys. KESLM:* shows all your cached LLM responses. The TTL command shows how many seconds remain before a key expires. The get command retrieves the stored value. The flushdb command deletes everything in the current Redis database, useful for clearing the cache during testing. The fourth code block shows cache invalidation helpers. Invalidation means deliberately deleting a cached answer before its TTL expires. You do this when the underlying information changes, and you want the next request to get a fresh LLM response. Next, common errors. If you see a connection refused error, Redis is not running. Start it with the Docker command from slide 5. If the source field always says LLM and never cache, your cache key is not deterministic. Check that you are using sort keys equals true in JSON dumps, and that all inputs are included. If users are getting stale answers, your TTL is too long for content that changes frequently. Reduce it or call the invalidate function when your source data updates. If users are getting other users' answers, you are caching personalized responses in a shared cache. Add the user ID to the cache key, or skip caching for personal queries entirely. If you get a module not found error for Redis, the library is not installed. Run pip install Redis in your active virtual environment. If Anthropic's native prompt caching is not reducing your costs, your calls are spaced more than 5 minutes apart. The ephemeral cache only lasts 5 minutes. If your in-memory cache disappears on server restart, that is expected behavior. Switch to Redis for persistent caching. Next, takeaways. 5 things to remember. The cache key must include the prompt, the model name, and the system prompt. All 3. Missing any of them causes wrong cache hits. A cache hit returns in about 1 millisecond with 0 API cost. A cache miss runs a normal LLM call and stores the result for next time. Set your TTL to match how often your content changes. Never cache personalized or user-specific responses. Use Redis for production because it survives server restarts and works across multiple server instances. Use an in-memory dictionary for local development because it requires no extra tools. Anthropic's native prompt caching reduces system prompt token cost to 10%. Add cache control ephemeral to any large, frequently repeated system prompt. Next up is video about tool calling, where the AI starts triggering real functions in your backend.